Okay, hello students, welcome to the class. We'll now continue with non-ideal solution. Non-ideal solution which you have seen. We have considered the solute and the solvent. Solute B, solvent A, both are liquid, both are volatile in nature. And non-ideal solutions are those in which solution and its component do not follow Raoult's law, that is PA is not is equal to P naught A into XA. Both components will not follow this law, that is vapor pressure of the solution, which we find out experimentally is not equal to what we get through the formula Raoult's law. And also the second point you have seen, delta V mixing will not be equal to 0, it will be either greater than 0 or will be less than 0. And the third, delta H mixing, change in enthalpy will also not be equal to 0, neither heat will be taken in nor given out. So we will be doing the px diagram and tx diagram for these solutions. So non-ideal solutions are of two types. Non-ideal solution is of two types. Solution which show positive deviation from Raoult's law and the solutions which show negative deviation. So which show positive deviation, in their case vapor pressure of this will be greater than the product of these two for both the component. And delta V mixing will be greater than 0 and delta H mixing will also be greater than 0 for this solution. And for negative, that is Raoult's law vapor pressure which you get through the experiment, that will be less than what we get through the law. And you can remember this. Second is delta V mixing will be less than 0 and the third, delta H mixing will also be less than 0. So keeping this condition in mind, we'll do type of non-ideal solution, Px and Tx diagram. Px diagrams are given, Tx diagrams are given, Px diagrams are not given in your book, so see here clearly. So first we'll look for positive deviation. Solutions that show. So these are of two types. These are of two types, type 1 and type 2. So what is type 1? If we draw px diagram, so we are going to do px diagram for type 1 solution. What is type 1? Solutions which show positive deviations. So for that you will have to plot a graph. I draw a little smaller so that both the diagram can be drawn parallel. To each other. Since this is Px, so we will keep temperature constant and pressure variable. This is for component A, this is for component B. Here is the composition. Composition can be mole fraction or percentage composition. So you know this side we will have XA is 1 and XB is 0, and here we will have XB 1 and XA 0, 100% A and 0% B. Here 100% B and 0% A. Always this will be taking throughout. So for Px diagram, as we have considered, component A we have taken with the low vapor pressure and this with the high vapor pressure. So first we will draw for ideal solution and then we will compare its deviation. So last time in the previous one you have seen, if we obtain a straight line, then I hope you remember this graph. So this is your P total for solution, which is partial pressure of A plus partial pressure of B. This line is indicating partial pressure of component A, and this point is P naught A and this point is P naught B. Vapor pressure of the pure component, vapor pressure of the pure component A, this is vapor pressure of the pure component B. And if it is a straight line, it is ideal solution. For non-ideal solution, type 1, what we have, that the vapor pressure of the solution of component A, if you see that, it will be showing a curve upward. Means with PA, partial pressure of component A, is more than the ideal condition. What we get experimentally is greater than the value we obtain through the law, Raoult's law, for both the components. So this is like this. And in this case, little you have to be careful. For solution also, it will be, vapor pressure will be higher, but at no point it will be greater than the vapor pressure of the component which is more volatile. So this line which you will be taking up will not indicate this curve which you are getting. This is for P total, and so this P total here, this is P solution is greater than PA plus PB, but at no point you find that the vapor pressure of the solution is more than the P naught B, more than the vapor pressure of the pure component which is more volatile. So this is Px diagram, and for the same we will be drawing Tx diagram. So here I do for you the Tx diagram. So I rub it here, this is all. and another graph. Okay, I use another color. You can draw in your notebook. If you draw and you prepare your own notes, you draw it and then you understand and make the notes, you will be understanding, remembering it in much better way, and the concept will be more clear to you. So now this is for TX diagram. So if Tx, then temperature is variable, so pressure will be constant. Pressure constant. And here it is composition, mole fraction, exactly the same way as we have done in previous diagrams, or percentage, here component A, here component B, here XA1, XB0, 100% A. Every time you have to write this, 0% B, and here XB is 1, XA is 0, 100% B, 0% A. So for this, if you draw this, although you have not to do in much detail this, but still if you do this, then this diagram will be reversed. Here P naught A, so this is lower, this is higher. This is P naught B. So when we draw for this, it will be A is having lower vapor pressure than this. It means boiling point of component A will be more than the boiling point of this. And you can draw the figure. But TX diagram for this PX type 1 is not in your syllabus. Why? Because this almost behaves like ideal solution. Almost, is not exactly like ideal solution, but quite closer to the ideal solution. So PX diagram for type 2. PX diagram for type 2 I'll do for you, and so here in this I do that. Draw again this box. Rest of the things will be the same. Here composition, mole fraction, and here is percentage, and rest of the things are same. I am not writing it again and again, and when in your notes you can do it. So this is P naught A, and so in type 2 again you will have to take first the ideal solution condition for PX diagram, because we have to compare. Type 2 is also showing positive deviation, and this is your for solution, a straight line we have obtained. So when it is type 2, we have this above it, and in the case of the solution, total pressure of the solution, it is found that at one point, that point you will have to take towards the higher side where the component is having more vapor pressure. So we will be decide a point is there where vapor pressure of the solution is more than the vapor pressure, higher, quite high, higher than the vapor pressure of the component which is more volatile. In the type 1 you saw at no point vapor pressure of the solution was more than the vapor pressure of the component which is more volatile. So this is type 2, and here you this point at which vapor pressure at this particular composition, if you take it at this composition, they have this much of the vapor pressure. Means more amount of this and less amount of A, and at the when we have this mole fraction or this much percentage, approx your 80% B and 20% A, then we have so much of the vapor pressure. So this is your type 2. So type 1, at no point vapor pressure of the solution will be more than the vapor pressure of the pure component which is more volatile. But in type 2, the vapor pressure of the solution at least at one point will be more than, at least at one, will be more than the vapor pressure of the solution, vapor pressure of the component which is more volatile. So for this we will draw TX diagram. This is there in your course. So for TX diagram, as I told, this is having low vapor pressure, so this will be having higher boiling point. So this is your T naught B for component A, and this is T naught B for component B. So ideal gas condition, ideal solution, you know that a dilute solution behave like gases. This is for ideal solution. Now if we convert this to this, so in that case what it will be, we will have a point, or we will have a fraction, mole fraction, where the vapor pressure, the boiling point of the solution, this line is indicating boiling point of solution. Boiling point of solution at one point is less than the boiling point of the component which is more volatile. Boiling point, this one component is having so much boiling point and the other component is so much. So the solution will have a boiling point less than the boiling point of the component which is more volatile, or the component which has low boiling point, pure component. So in that case we will have the graph like this. We'll have the graph like this. So this point is marked with M, and here M is, now you can compare the two diagrams, and why I have drawn parallel, you should know to recognize what composition. This one was Px, this is Tx, and so point M is indicating minimum point. What minimum point? If you draw a perpendicular from here to here on the temperature axis and the composition axis, so what this point indicates that at this much of the boiling point, this will be TB, boiling point of the solution with mole fraction, say the mole fraction is A, at A composition, is minimum. So when the solution, this type of solution, they reach to a fixed composition, fixed mole fraction of A and B, or the percentage of A and B, then they will have a minimum boiling point. And such solutions are called minimum boiling solution, and are also named as a azeotropic solution. Also named as azeotropic solution. So this was your type 2. Now, the reason for this, we'll see. The first reason, if you will see, what is that? You have seen that vapor pressure of the solution is higher at one point. So why it is there? Because the intermolecular interaction between what? A and A and B and B, which is giving you A and B. If this interaction is A, this interaction is B, and here this interaction is C, then A may be equal to B, may or may not be, or this, but surely A is equal to B, then it will not be equal to C. Or it may be A is not is equal to B, is not is equal to C. Means interaction between these two components when they have formed solution is not exactly the same when they were having interaction in their pure state. So in that case, what will happen? The interaction force, interaction between components in solution is weaker. Means A and B, solute and solvent molecules, they are not held tightly, because of which this solvent particles which are not held tightly will be evaporating faster, will be going to the vapor phase faster. So vapors formed will be more, and so what will happen? That is PA will be greater than P naught A, XA, PB, this will be into XB. This is because of the weaker intermolecular interaction between the components in the solution. So first point, that they do not, the component and the solution do not follow Raoult's law. The second is delta V mixing will be greater than 0, will not be equal to 0. You have done that. This will not be equal to 0. But in this case, type 2, it is found to be greater than 0. So why greater than 0? If the volume of A molecule is so much, volume of B molecule is so much, and the solution formed is having this much. So the volume occupied by the molecules in solution of components is more than their original volume. Then we have this. Final volume is more, initial volume is less, so difference will be positive. So delta V mixing will always be positive. Why this was there? The reason is same. Intermolecular interaction is weak, so they occupy more space. A was having this much, B was having this much, so this should have that if the volume of this is A and the volume of this is B, then volume of this is, if it is C, then A plus B is not is equal to C. What it is, A plus B is less than C. This is the case. And so, this is the unit. Now see the third point. Delta H mixing is also equal to 0. That is, delta H mixing is not equal to 0. What does it mean? It means that A and A molecule and B molecule, when they are this one molecule of A, the other molecule of A held together, so their binding for interaction force is stronger and stronger. And here AB which is formed and then binding force is not that stronger. So these interaction forces are when stronger, they will absorb more energy. So energy absorbed is more for departing these molecules. This is not a chemical bond, so I am using the word molecule. They are held together by interaction force. So energy absorbed to get these molecules separated is more, and the energy evolved when these two are coming close, different molecules, and establish a new interaction force. Old interaction force is getting broken, new interaction force is going to get formed. So when a new interaction force is forming, energy is evolved. So energy is evolved. Since this is weak, this force is weak, energy is evolved less. Force is weak, energy evolved is less. Force is strong, energy absorbed is more. So energy absorbed is more than the energy given out. So the net reaction, the next process will be, net will be what? Endothermic. Heat will be absorbed, net process. So in that case, what will be there? Delta H mixing will be positive. I hope this is clear. Now we come to the type 3. PX diagram for type 3. What is type 3 solution? Which show negative deviation. So we will plot the graph PX diagram. The same that thing we have to do. If you draw again and again and again, don't be lazy student to draw this figure. If you draw and then you prepare your notes and you teach to yourself, you understand and study, it will be more convenient and easy for you to remember. It is PX diagram, so temperature constant, pressure variable, here composition. What composition? Mole fraction, or what else? Percentage. Here component A, here component B. Here mole fraction of A is 1, mole fraction of B 0, 100% A and 0% B, and here XB is 1, XA is 0, 100% B and 0% A. We have taken this low volatile, less volatile, and this is more volatile. So this was P naught A, this is P naught B. So we will draw first ideal condition to compare the deviated condition. Now for the solution. In this case, the vapor pressure of solution at one point will be quite less than the vapor pressure at this point. The vapor pressure of the solution, this is vapor pressure of the solution, this curve is also, this is your minimum. So vapor pressure of the solution at this point is minimum, less than the vapor pressure of the pure component, which is less volatile. Vapor pressure of this component in the pure state, which is less volatile, is so much. So when it is forming solution with B, then solution will have at this point its vapor pressure less than P naught A value. So if we draw the TX diagram, for the same, so now TX diagram for type 2, exactly, showing negative deviation. So draw it. This is Tx, so pressure constant, and temperature variable, for this. And temperature variable, where is composition for A and B. You write all that. XB is 1, XA is 1, and rest all you write. I'm not writing. Okay, and so in this case, this was having low vapor pressure, so this will have a higher boiling point. This is having higher vapor pressure, so this will have a lower. So first we will draw ideal condition to compare with the deviated condition. So this is the ideal condition, and in this case it is what found that the boiling point, this point is boiling point of component A, and this is boiling point of component B, and this line is indicating boiling point of the solution. So when this is the condition, negative deviation, in this case what will happen? The vapor pressure is low, so the vapor pressure of the solution is low at that point. So at that particular point, at this composition, and this pressure. At this composition, the pressure is so much least here. So at that particular here, reversed, lower will be higher. So we are coming to the higher side, so we will remain towards the higher side. So at this point is maximum. This is gone. This is gone to higher. Higher point you will draw on the higher side. Higher point you will draw on the higher. So this is the point at which what it is at this particular composition and at this particular temperature. This temperature is TB of solution. So when this solution which we have here, this is your non-ideal solution, and at this particular point, this is for the solution at this particular point, when composition is so much, say the composition is B and the boiling point is TB. TB is the boiling point at the composition C. What is there? The boiling point is maximum. So when the boiling point of the solution is maximum at this composition, then this is called maximum boiling solution. Okay. So type 2 is maximum boiling solution, and this was type 3, not type 2, this was type 3. Type 3 is maximum boiling, type 2 is minimum boiling, and type 1 is closer to 1. So type 1 doesn't show any point where it is maximum. Only in type 2 and type 3 you saw minimum in type 2 and maximum in type 3. Minimum what? Minimum boiling point in type 2 and maximum boiling point in type 3. Maximum vapor pressure in type 2, minimum vapor pressure of the solution in type 3. Now we will see the reason for this. The reason is exactly like what we have done for type 2. What is that first condition? That is PA is not equal to the product of these for non-ideal solution. Why is there? We have A molecules and B molecules giving you AB molecule. If interaction forces between AA molecule and AB molecule is not same. Now here, if this is having some interaction force say A, this is having some interaction force say B, some interaction force say C, then A is strong, maybe equal to this, or it will be A may be greater than this, or A will be less than B. But definitely A, if these conditions A and B are less than, now look here. A and B is what? Interaction force of this and this. So A and B, this is if this is the condition, A is equal to this. But when AB are combining, interaction force which is establishing here is not equal to so much, but it is less than. So, but when A and B interaction forces are more than the interaction force of C. That is the condition. Means what? These are held very tightly. So when interaction force is stronger in solution than the pure components. Then the pure component, when this is stronger, what will happen? In that case, they will not be forming, they will be held tightly, will not be easily able to go in the vapor phase. So vapor's form will be less. That's why they will have low vapor pressure, as we have seen in px diagram. So in that case, what we will have? This will be less than this, what we obtained from Raoult's law second. Delta V mixing will be less than 0. Again, that is volume of A is so much, volume of B is so much. When they form AB, volume of this is so much. If volume of this is A, this is B, and this is C, then A plus B is not equal to C. That is there. Not only is equal to, but A plus B is greater than C. What it is? Volume occupied by solution molecules, by molecules in solution, is more than the pure component. So if they are occupying, is less, not more, this is more, this is less. If they are occupying less, very much compact, less space they are coming, less than the pure component solution. In solution, molecules are occupying less space. So they are very close. When close, then interaction forces are stronger, as we have seen in the previous case. So what will happen? In that case, delta V mixing will be negative. Now the third point. What is the third point? Delta H mixing will not be equal to 0. So what is that? Again, here you have seen volume occupied by molecules in solution is more. Because of that, they have strong interaction forces in the molecule, and because of which what will happen? Just see here. Here they are, the interaction force is weak. A and A and B and B. This is weak. They are far. So here A and B, they are stronger interaction forces. And you see the interaction force in AB. So A has got interaction force A, B has got interaction force B, and AB has got interaction force C. So this interaction force, this C is stronger, this is stronger, and this is weaker, stronger, this is interaction force. So this is weaker, it means what? When they will be getting departed, A molecules will be getting departed, they will absorb less energy. B molecules are weaker, so they will absorb less energy. They are stronger, so what will happen? You know that when bond gets separated, force gets separated, molecules are departing, what happens? They absorb energy. So energy absorbed this side will be less because the interaction force is weaker. Here interaction force is stronger, so energy which is evolved, energy which is given out, that will be what? More. So energy evolved will be more, energy evolved is more, and energy absorbed is less. what will happen? An anti-word is more, so the process will be exothermic. So the process will be exothermic. Means what? Delta H mixing will be negative. What is that? Delta H mixing will be less than. So that's all about the condition and the PS and TX diagram. And next now we will do that fractional distillation. So till then, bye.